everyone. It's going to be a huge shift. So if you are planning a trip to the deep ocean, you should know the forecast. It's going to be cold, dark, and probably snowy. And by snow, I don't mean ice crystal snow as we all know. Marine snow is a type of microbial aggregates. Microbial aggregates are basically clusters of tiny microorganisms, in this case, algae and bacteria. The surface water in the ocean is full of these tiny microorganisms. Their bodies stick together in a close-knit community, via extracellular matrix, or in short, ECM. It's polymetric network that's composed of polysaccharides, proteins, extracellular DNA, and basically, when they are arriving or reaching this critical biomass, they're creating little globs, and they will eventually sink to the bottom of the ocean. You can see them here in the image. They're pretty small, and they are tiny and very much important. And why they are important? Because in the creation of marine snow or other mucilage event, we are basically causing a nutrient depletion or organic matter depletion from the surface water, and by that we are potentially inhibit the phytoplankton growth on the surface water. The phytoplankton is much more important for photosynthesis processes. And also, another reason it's important, by creating this aggregate, we are creating very unique chemical microenvironment where cooperative emerge, and these tiny microorganisms creating this, creating a new, creating new functions as a result of these cooperative and interactions. Another very important reason is that this microbial multicellularity are basically small ecosystems. Now they have functions that they didn't have before because this very unique environment in a closed system. Until recently, phytoplankton were considered the main producer of the ECM, and the bacteria only colonized this substrate. But now this view is shifting. Actually, in our lab, Dr. Valeria Lipsman showed that the bacteria play much more significant role in the production of the ECM. And by that, it opened a question, and our question, how do microbial interaction influence the extracellular matrix within algal bacterial aggregates? So we saw that algae alone create these little clusters. But when bacteria added to the culture, they are creating even bigger clusters, aggregates. But here we are seeing algal bacterial interaction. But what about bacteria-bacteria interaction within these aggregates? And our approach to address this question is by syncoms. Syncoms are synthetic community. In our case, algae and bacteria. So syncoms provide controlled yet controlled laboratory setting model that have the sterile environment in the lab, but yet have much more closer complexity to the environment, to natural aggregates. So we are adding algae and few bacteria. So the first stage to create the syncom is to choose the different participants. So the first one is Emiliana Huxley, which is in short EAX. It's the most abundant microalgae in the ocean, causing oceanic blooms, and play a critical role in biogeochemical cycles. And the bacteria I chose to interact with this algae are bacteria that we know that found in the phycosphere of this algae in the ocean. So the first one is P. inhibans. P. inhibans in some conditions can promote algal growth, but some conditions can be pathogenic. We also chose Rogeria species that can enhance the production of polysaccharide that the algae produced. So for me, for the ECM aspect, it's very important. We also took Marinovum algicola, which can improve algae uptake in nutrients. And we added also to the mix the Sulfitobacter pontiacus, that also from previous research in our lab by Ronnie, a PhD student. She found out that Sulfitobacter pontiacus can protect EACs from the pathogenicity of P. nabans. And we also took Dinoroseobacter shivae, which also can increase algal survivors against pathogens and parasites. So now we chose all our participants, and I need a way to count and detect all of them in my SynCom. For that, most of the time we are doing sequencing or qPCR, but these ways, although they are very much reliable, think about these all bacteria, they are practically family, they are cousins, so they are very much similar. So these techniques are a bit problematic if I want to manipulate my system. So to track them, I use selective plates. So selective plates are media that allow only one bacteria to grow on them. So this is all my bacteria, and I scan many mediums. But these are the most successful ones. And they allow the growth of only one bacteria in my SynCom. So now that we know how to track them, I want to do one more thing before I will create my SynCom. I want to see how they interact with my algae. So I created core culture. So it's a lot of graphs. Let's focus on one of them. So this is P. nabans with the algae. In bars, we can see the amount of algae in the core culture, and the dashed line is the bacteria. Through 14 days of co-cultivation, we can see that the P. nabans is a pathogenic towards the algae because we see the decline on the day 14. So if we go back to the all co-cultures, we can see that we have two pathogenic bacteria, P. nabans and Rogeria. So now that we know how each of bacteria interacts with the algae, I'm going to my SynCom. So here is my SynCom. We can see in the lines the bacteria, the different bacteria, and the bars, the algae. And we can see something very special, that although we have two pathogenic bacteria, the algae is still alive at day 14. And that's very important. Another thing that I can see is that the whole system reached to stationary phase approximately at day 6, which is very important to me, because according to the literature, in this stage, this phase, there is a massive production of ECM. And that actually leads to my next step, to look much closer on the ECM. So I want to give you a small taste of something that we are doing. I took my flask on day 10, and we can see small aggregate on the bottom of the flask. But we also can notice that the liquid is a bit viscous, probably because of the polysaccharide secretion from the ECM, from the aggregate. So I'm using this medium as a proxy of my ACM, and I'm measuring that viscosity. So we use increased shear rate, and by that I mean we took the medium and we squeeze it and try to break it and see how the sample resists to be broken. And these shear rates are very much important and relevant in terms of the ocean, because 0.01 is when the ocean is calm, that's the shear rate, and 10 is when the ocean is very big. So we look at just the algae alone, and we see very low viscosity and very similar to water. When we add in the core culture, the viscosity increase in some cases, in the peanut buns and the rogeria. But something very important, when we increase the shear rate, the sample breaks. And by that, the interaction there probably are more weaker. But when we look on the synchrome, the pink line, we can see that although we increase the shear rate, it stays stable and pretty high. And if I will go back to my question, how do interaction within algal bacterial and bacteria affect the interaction, the ECM, we can see here a first clue that there is an effect. And how this mechanism works, that's what I want to find out. So now that we have the synchrome, I want to see much closer on the ECM composition and structure and understand who produce which sugar. I want to deep dive to the microenvironment, especially pH and oxygen level, and to examine how the bacterial physiology within these samples, and maybe in the future to take natural aggregates and implement them in this system that we see. And with that, I would want to thank my lab for the help and support. Especially thanks to Dr. Reinat Segev to being my mentor, amazing mentor, and to Eliana that gave me the permission to play with her toys in the lab. So thank you.